I would go the interval 4 to 6, and the midpoint of 4 to 6 is 5, so V of 5 is 13 times 2. Six to 8, I would use the midpoint of that, which would be V of 7, and V of 7 is 6. Let's see, we got 26, and we got a 12, and finally 8 to 10, I would be using V of 9, and V of 9 is 6 as well. All right. Now, by the way, the answer for what this accumulates is the same thing. This is another representation of the distance of the train in the first 10 seconds. What does this one give us? .94 inches. Okay. So do you feel like you have a better idea of how to do a midpoint then? Okay. In something where the function, in something like this, where you guys said, hey, I could tell from the graph, but if you don't have for sure what the graph is, you would actually plug in that value into the function to find its height. Okay. All right, let's talk about a trapezoid. Some textbooks, even our textbook, they have like this formula for trapezoid rule. I don't like to memorize formulas because there's already so many things we have to memorize in calculus. I just like us to just remember what the formula for a trapezoid is, and we're going to add up the trapezoids. Okay. So first of all, you may or may not remember the formula for area of a trapezoid. So here it is. Okay, it's area equals 1/2 height, and then B1, B2 would be the average of the bases. Let's label some things on here. This is my B1 and my B2, and the height is the distance between those. Essentially what if you remember from geometry, or probably you guys did this earlier on than geometry, the idea was like you're averaging two rectangles together. That's kind of because they're two different values. Or you can think of it as, because I have a triangle and a rectangle, you're adding those two things together. Okay, so if the area of the trapezoid then is that, but when I'm doing this on a curve, what happens is I'm flipping this trapezoid like this. Okay, so how am I going to figure out what B1 and B2 are? B1 and B2 are going to be, remember our rectangles? They're going to be the sides of our rectangles, or the functions. And then the height would be the width of the interval in these. So essentially what we're doing is, let's go back to something like this. When we did our rectangles the other day, what a triangle or what a trapezoid would look like is if I went from 1 to 3. We had cut these in half. If you would make, or you would find the height of the curve at 1, the height of the curve at the other, and we're essentially cutting that on a straight angle. Do you see how that becomes a better estimate than what a rectangle was? Because it at least is cutting that curve on a diagonal. So then if I was doing this one, this is a trapezoid, not an MRAM, so I'm just using this for drawing purposes. Pretty steep one. I know my drawing's not the best, but you get the idea. Okay, so trapezoid would be probably on that a better approximation than the midpoint Riemann sum as well. Okay, so that's what it looks like. So what we're going to need to do then, and here is where you could use a shortcut if you want. What is one thing that is going to stay the same throughout in this formula? The 1/2 is. Easton, in this case, the H is also going to be the same, but be aware that sometimes I'll do it in a table and I'll make them unequal, okay? The reason why I'm pointing that out is when we get to the calculator part, let's make our lives a little easier by using distributive property, okay? But I'm still going to write out the answers. All right, so we are going to use 4 trapezoids from 1 to 3. So this is what I was just doing here. Here's 1, 2, and 3. We're going to cut those each also in half really, really carefully. Okay. The first one is going to be from 1 to 1.5. So if I wanted to draw that trapezoid, I would see, I would figure out what f of 1 is, and I'd figure out what f of 1.5 is, and those would be my bases. Okay. So it would be 1/2 times the height. The height would be also 1/2, right? Isn't the distance between those bases 1/2? And then these would be the average of 1 plus, hey, from a previous page we probably did this, but what happens when I plug 1.5 into the equation? We did this, didn't we use the same curve? It's 1.25. Okay. The trapezoid from 1.5 to 2 is going to be 1/2, that comes from the formula, times 1/2, that comes from the width of the rectangle. And the bases on this one, let's draw this trapezoid, are going to be 1.25 and 2. All right, let's do the trapezoid from 2 to 2.5. So it's a really steep one. So we have the area would be 1/2 times 1/2. The bases on these are 2. What happened when we plugged 2.5 in earlier? What did we get? We can do it. $3.25. And finally, from 2.5 to 3, so there's that trapezoid. We have 1/2 times 1/2 times 3.25 plus, was this 4? 5, looks like. But I will check. Okay. On something like this, guys, do you see how over and over I have 1/2 times 1/2? So if I wanted to save some time on that, what I could do is I could do 1/2 times 1/2, which ends up being 1/4, and then times 1 plus 1.25 plus 1.25 plus 2 plus 2 plus 3.25. Do you get, I'm just using distributive property here. Plus 3.25 plus 5. All right, let's do that. In other words, couldn't you do that stuff and then divide the whole answer by 4 to save some time instead of doing it individually? Okay. Furthermore, if you want to save some time, do you notice besides the first number and the last number, there's double of each number because they're each part of a one of the bases. So you could multiply those by 2 if you want. All right, so I think what I'm going to do is 1 plus 2 times 1.25 plus 2 times 2 plus 2 times 3.25. But at the end, there's only 1. So the first base and the last base, there's not double of because they're not on an interior. I got 19. I divide that by 4. I got about 4.75. Okay. Okay. By the way, if you're going to be a math major or you're going to be an engineer and you end up taking like Calc 3 and above, there is another way, but it's not an AB or a BC topic, that instead changes trapezoids to curves, and it's called Simpson's rule. Just know it's out there. If you're asked anything about Simpson's rule, if I assign bookwork or whatever, you should ask me about it because it is not an AB topic. Okay, so we're not going to cover it. But would we agree that the trapezoid is better than the rectangles? What would be better even yet is there is a way to do like a trapezoid with a parabola top, because that would be a curve. That's what Simpson's rule is all about. Okay, so let's pull out then our worksheet. The first thing that I want us to make sure we do is we're going to do B, because I told you weren't doing a trapezoid yet, but now we are. So we're adding 4B to the mix for a trapezoid approximation. And then we are finishing all of the 5-1 questions. So just be aware, and question 6, you go ahead and use your calculator to sketch regions. You're going to also use your calculator for the intervals because you're going to have to plug them in to figure out how high they are, okay? So calculator abounds here, lots of calculator. That's going to take a good chunk of time because I asked you to do only 4 rectangles, but I asked you to do left, right, middle trapezoid. Okay. Number 7, you're using your calculator. You're going to find the cost of producing 200 kilograms of cheese. This is going to be exact. Do you know why? Has to do with this. What kind of function is that? It's a line. If I have a line, it's going to have a negative slope. Wouldn't a trapezoid fit it perfectly? Making sense? Okay. So you actually don't even have to break it into trapezoids. You can do one big old trapezoid on that one. Number 8. Just a conceptual question. 9 is also a line again. You can either use a triangle or trapezoid, I don't know. 10, ooh, interesting. Like it.